Continuing our conversation on exponential functions and compound interest rates, let's take a look at a situation where we're compounding $1 for 100% over 1 year. And we're going to take that information and see what happens if we increase the number of compounding periods, n, per year that we're compounding the money. So I've got a table down here with a list of values for n. We're just increasing by a factor of 10 each time to see what happens. If you're here and you haven't had a chance to fill in this table, pause the video, go back and fill it in, work out that problem one number at a time, and then come back and we're going to take a look at all of these numbers together. All right, we're back. Hopefully you had a chance to fill out the table now. And let's take a look at what happens. So we plug in 1 and we get 2. We plug in 10 and as expected we get a little bit more. But notice as we increase n that our digits compared to the previous one, it seems like we gain a digit each time compared to the previous one. But it's not changing very much. And we lost that last digit compared to the previous one. So we're actually approaching a number 2.7182818284590445, and it goes on with lots of other numbers. This fixed number has been given a name, and that name is E. This is an irrational number, similar to pi. It never repeats, it never ends, it goes on forever and ever. And also like pi, E shows up a lot in a lot of different places. It's also known as Euler's number, because the mathematician Leonhard Euler is credited with discovering this. This expression of the 1 plus 1 over n to the n power, it gets closer and closer to that fixed number. If we increase our compounding periods to infinity, we call that compound continuously. So we can look at compounding interest continuously, which means even more than every second, the interest is going into your account. And since we found that this special case of investing $1 at 100% would lead us to E, it actually turns out that this compound interest formula, if we increase n to infinity, leads us to our continuous compound interest formula. A equals P times E to the power RT. How do we relate these? If n is a finite number, or if we compound annually, or monthly, or weekly, or daily, or semi-annually, or bi-monthly, or any of those other ways that we could compound, then we're going to use our compound interest formula, P times 1 plus R over n to the power nt. But in the problem, if we are told that we are compounding continuously, then we would use A equals P times e to the RT. Looking at an example, find the amount of money accumulated if $1,000 is compounded continuously at a rate of 8% for 5 years. Notice the key words, compounded continuously. That leads me to use A equals P times e to the RT. And sometimes I've heard students call this the Pert Formula, P-E-R-T. One way to help you remember it. And we can plug in our numbers. P will be 1,000. Our rate is 8%, so that'll be 0.08. and our time is 5 years. And that E is going to be the E in our calculator. It should be a button. So 1,000 times E to the exponent 0.08 times 5. And I'll pull up my scientific calculator here. Your E button might be near that natural log button. So if you're on your calculator and you're looking for E, try to find your LN button, the button that has the LN on it. Try to find that button because the E will be very close to it. So let's try this out. So 1,000 times E to the exponent. I'm going to use a parentheses because I need both of them in there. 0.08 times 5. I'll close my parentheses. Notice 0.08 times 5 is 0.4. And then we'll hit enter. $1,491.82. And that's how much money I would earn in 5 years, compounding at a rate of 8% continuously. It actually turns out that this exponential function e to the power x has a really special property. E to the x is this green function in the middle between 3 to the power x and 2 to the power x, as it should be, since e is approximately 2.7. So it'll fall in the middle between 3 to the x and 2 to the x, except closer to 3 because 2.7 is closer to 3. It can be used as a base for any exponential growth or decay problems. And we can just plop the rate right in there. And the big idea behind that, we would go back to this function a equals p times e to the rt. And if we had some rate of growth or decay, we can just plop it there. And then the p would be our initial amount. How much do we start with? So this idea that e to the x is the natural exponential function, it has lots of reasons, some of which are beyond the scope of our class, but it does show up a lot in natural phenomena, in any exponential growth or decay problem. And so we'll be exploring this particular base throughout this chapter, as it's a pretty important number for exponents.